Welcome back to the Deep Dive. We're the show that takes, really complex research and boils it down, gets you the insights you need.
And today, yeah, we're diving into something pretty mind-bending. We're looking at how artificial intelligence is becoming absolutely essential, not just helpful, but essential for tackling the universe's biggest unknowns.
Right, the big ones. We're talking dark matter, dark energy, basically the 95% of everything that's invisible.
Exactly. It's a frontier where just building bigger telescopes isn't enough anymore. You need smarter ways to analyze the light you do get.
So our mission today is really to unpack how AI went from maybe a fancy data sorter to a genuine research partner. We're talking industrial scale discovery, precision that people probably didn't even think was possible a decade ago.
Yeah, and the sources we're drawing on today really cover the gamut. We've got foundational stuff like the Dark Energy Survey, the just sheer scale of the newer DSI map,
DSI, yeah, we'll get into that.
and even these specific, really cool discoveries like exploding stars caught literally in the act, purely because an algorithm flagged them.
Okay, so before we jump into the AI specifics, let's just quickly recap the scale of this invisible problem for everyone listening. Why is AI even necessary here?
It really comes down to the cosmic inventory. Everything you see, every star, every galaxy, all the gas and dust. That's what we call normal matter.
The stuff we're made of.
The stuff we're made of, yes. And it accounts for only about, well, 5% of the total mass and energy in the universe.
5%. That number always gets me. It feels fundamentally wrong somehow.
It is profoundly strange. So the other 95% is the dark sector. You've got roughly 70% dark energy, this mysterious force pushing space itself apart, making the expansion accelerate.
Which we still barely understand.
Barely. And then about 25% is dark matter. This is some kind of invisible particle, we think, that doesn't interact with light but does have gravity.
Yeah.
It's like the hidden scaffolding holding galaxies and galaxy clusters together.
So the challenge is, we're trying to figure out the nature of 95% of reality by looking at the tiny wiggles and effects it has on the 5% we can see. That sounds inefficient.
Extremely inefficient if you're just using human eyes and traditional methods. The signals are incredibly faint, buried in noise. You need something that can process vast amounts of data, spot subtle patterns humans would miss, and do it fast.
And with incredible accuracy.
That's the key word. It's not just about handling the data deluge, though that's part of it. It's about achieving a level of precision in the measurements, filtering out errors, understanding the statistics. That's where AI really shines. It's giving us almost a new sense to perceive this invisible structure.
Okay, let's get into that. This core challenge, measuring dark energy and dark matter. You mentioned the Dark Energy Survey, DES. That seems like a good place to start.
Yeah, DES was a major international effort. Their goal was ambitious. Map the distribution of all matter, dark and visible, across a huge chunk of the sky, looking back about 7 billion years in cosmic time.
How do you map something invisible, though? What's the technique?
The workhorse technique is called weak gravitational lensing. It's really clever, actually.
I've heard the term, but break it down for us. How does lensing let you see dark matter?
Okay, so, Einstein told us gravity bends light, right? Imagine light traveling from very, very distant galaxies, billions of light years away. As that light travels towards us, it passes through regions of space that contain matter, both normal galaxies and clumps of invisible dark matter.
Okay.
The gravity of that intervening matter, the foreground stuff, acts like a lens. It slightly bends the path of the light from the background galaxies.
So the images of the distant galaxies get distorted.
Exactly. Their shapes get slightly stretched or warped. Now, here's the catch. The weak in weak lensing is important. The distortion for any single galaxy is absolutely tiny. It's often much smaller than the galaxy's own natural random shape.
So if you see a slightly squashed-looking galaxy, you don't know if it was born that way or if dark matter squashed its image on the way here.
Precisely the problem. You can't tell from one galaxy. The power comes from statistics. DES looked at something like 100 million background galaxies.
100 million.
Yes. And they analyzed the shapes, looking for tiny correlated alignments or stretching patterns across large regions of the sky. If you see thousands of galaxies in one area subtly stretched in the same direction, statistically, that tells you there must be a massive amount of foreground matter, mostly dark matter, doing the lensing.
So you average out the randomness to find the underlying lensing signal. That's statistically intensive.
Hugely intensive. And from that statistical signal, they could build up a 3D map showing where the clumps of mass, including the dark matter, are located.
And DES did this for a big patch of the sky, right?
Yeah, about a quarter of the southern hemisphere sky. a monumental data set. But the AI breakthrough came next, from a team led by University College London UCL. They took this existing DES map and applied machine learning to squeeze even more information out of it.
How did AI improve on the map that was already built? What did it do differently?
This is where it gets really interesting. It's about precision. The UCL team didn't just look at the map. They trained their AI using simulated universes. They created thousands upon thousands of slightly different model universes in a supercomputer.
Running the universe over and over again with different settings.
Kind of. Each simulation had slightly different starting conditions. A bit more dark energy here, a bit less dark matter density there, maybe a different expansion rate. The AI learned how those fundamental cosmological parameters affected the patterns you'd expect to see in the weak lensing data.
So it learned the connection between the universe's recipe and the final lensing look.
Exactly. But crucially, it wasn't just about recognizing shapes. The AI got incredibly good at modeling something called the covariance matrix. This is a complex statistical tool that describes all the uncertainties and, importantly, how the errors in different parts of the map are related to each other. Getting this matrix right is vital for accurate results, and it's something traditional methods really struggled with for a data set this large and complex.
So the AI wasn't just faster, it was fundamentally better at understanding the noise and the statistical quirks of the measurement itself.
That seemed to be the case. It provided a much more robust way to handle the uncertainties inherent in the weak lensing technique.
And the result? What was the payoff for using this AI-driven statistical approach?
This is the headline number. It doubled the accuracy of the measurements for key things like the total amount of dark energy and the overall density of matter in the universe, compared to the previous analysis of the same DES data.
Doubled the accuracy, just by using a smarter analysis method.
Just by using smarter analysis, think about what that means. Doubling the accuracy lets you narrow down the possibilities for what the universe is made of. You can start ruling out theoretical models that might have been plausible before, but are now inconsistent with this more precise data.
That's a huge leap, and it connects to the efficiency argument too, right? I remember reading something startling about that.
Oh, absolutely. Dr. Neil Jeffrey, the lead author on that UCL paper, put it very starkly. He said that to get that same factor of 2 improvement in accuracy without using their AI techniques,
Yeah.
they would have needed 4 times the amount of data.
4 times. So instead of 100 million galaxies, they'd have needed to map 400 million.
Pretty much. Map another 300 million galaxies. Imagine the cost. Billions of dollars, probably another decade of telescope time on world-class instruments. The AI essentially gave them that boost for free, just by being smarter with the data they already had.
That's an incredible return on investment. It's like upgrading your telescope massively without touching the hardware.
Exactly. And it's not just a one-off result. We're seeing similar things from other groups tackling the same problem.
Like the ETH Zurich study.
Right. They used a different type of AI, a deep learning model specifically, a convolutional neural network, the kind often used for image recognition. They trained it purely on simulated maps of dark matter distribution. Their AI model produced estimates of dark matter density that were 30% more accurate than the standard human-designed statistical methods. Again, better precision from the same input data. They estimated this could potentially have the required observation time on telescopes for certain kinds of studies. The AI is just proving better at picking out those faint, complex gravitational patterns from the noise.
Okay, so AI delivers unprecedented precision, but that precision then forces us to confront what the data is actually telling us, which leads to this lumpiness puzzle you mentioned earlier, coming out of the DES analysis.
Yes, this is where it gets potentially paradigm shifting. The DES results, especially with this enhanced AI precision, suggest that matter in the universe today, or at least over the last 7 billion years they looked at, is distributed more smoothly.
Smoother.
Less lumpy than our standard cosmological model predicts it should be, based on what the universe looks like much earlier on.
Less lumpy than expected. Why is that a problem? Unpack that for us.
Okay, so our standard model, called lambda CDM, is built on Einstein's general relativity. It takes the baby picture of the universe, the cosmic microwave background, or CMB.
The afterglow of the Big Bang.
Exactly. The CMB shows us tiny variations in density in the very early universe, just a few 100,000 years after the Big Bang. Lambda CDM predicts how gravity should have caused those tiny initial density fluctuations to grow over 13.8 billion years, collapsing into the galaxies and clusters, the cosmic web we see today.
So the CMB gives us the starting conditions, and the model predicts how clumpy things should be now.
Right, but the DES measurements, looking at the universe much later, suggest that structure hasn't grown quite as much, or as aggressively as predicted. It's smoother, less clustered, less lumpy than the prediction based on the CMB starting point and general relativity.
Hmm. So the late time measurement doesn't quite match the extrapolation from the early time measurement. Could the AI be introducing some kind of bias? Maybe it prefers smoother solutions for some reason?
That's the absolutely crucial question, and why these results faced intense scrutiny. Is it a real physical effect or an unknown systematic error in the measurement or the AI analysis? People are definitely checking for that.
Of course.
But one argument is that these AI techniques were actually designed to be better at identifying and removing known systematic errors, things like atmospheric distortion, telescope calibration issues, stuff that can plague traditional analyses. The fact that multiple AI-driven analyses seem to point towards this smoothness makes it harder to dismiss as just an error.
Interesting. And you mentioned the DS findings still align with the simplest model for dark energy, the cosmological constant. How does that fit in?
Right, so the cosmological constant model just says dark energy has a constant value everywhere and throughout all time. It doesn't change. If dark energy did change, some theories call this quintessence, that could potentially affect how structures grow, maybe influencing the lumpiness. The DE's data seems consistent with the simple, constant dark energy model. But the lumpiness problem remains even within that model. The smoothness relative to the CMB prediction is still there.
So if it's not dark energy doing something weird, what's left?
Well, that's the uncomfortable implication. If dark energy is simple and the measurements are right, it hints that maybe the issue isn't dark energy, but our theory of gravity general relativity on these enormous cosmic scales. Is GR the complete story for how structure grows over billions of years? Or does the observed smoothness point to something slightly different? That's the tension.
Wow. Okay, so this precision measurement, amplified by AI, might actually be pointing towards cracks in Einstein's theory. That's a huge claim.
It's a claim people are very cautious about, but yes, it's on the table. And to really resolve this tension, we need more than just precise average measurements. We need detailed maps. We need to actually see the structure.
Which brings us neatly to the next stage, using AI not just to measure properties, but to build these vast 3D maps of the cosmic web, including the dark components.
Exactly. We're moving from statistics to visualization, in a way. And AI is key here, too. Think about the work done on mapping dark matter bridges.
Dark matter bridges, that sounds cool, like actual filaments connecting galaxies.
That's the idea. We theorize that galaxies aren't just scattered randomly. They're connected by these vast, tenuous strands of dark matter forming a cosmic web. But seeing them is hard.
So how did they map them?
A team from the American Astronomical Society used AI, but they trained it in a specific way. They used a set of incredibly detailed computer simulations called Illustris TNG.
Illustris TNG, what's special about those simulations?
TNG stands for the next generation. These are state-of-the-art cosmological simulations. They don't just model dark matter. They include gas physics, star formation, black hole feedback, magnetic fields, basically all the complex astrophysics we know about. They run these massive simulations on supercomputers, evolving a chunk of the universe from the early times to the present day.
So it's like a realistic, simulated universe to train the AI on.
A very realistic training ground. The AI learns the complex relationship within the simulation between where the visible galaxies form and where the underlying invisible dark matter structures are the halos around galaxies and these connecting filaments.
Okay, so it learns that connection in the simulation.
And then they applied this trained AI to real observational data, looking at the distribution of actual galaxies in our local part of the universe.
And the result?
The result was a new map that remarkably clearly shows these filamentary bridges made of dark matter stretching between galaxies. It's perhaps the most direct visualization we have, confirming that these predicted structures are real, that dark matter really does form the gravitational backbone of the cosmos.
That's incredible, seeing the invisible structure. But that was focused on the local universe, right? For mapping on the grandest scales, we need to talk about DSI.
Yes, DAI, the Dark Energy Spectroscopic Instrument. If DES was about precision, DEAI is about scale and speed. Their recent first major data release, DR1, is just staggering.
Give us the numbers. How big is this map?
Okay, so DR1 covers the first 13 months or so of their main survey. In that time, they gathered detailed data spectra for 18.7 million objects.
18 million.
Million. That includes 13.1 million galaxies and 1.6 million quasars, which are super bright cores of distant galaxies powered by black holes.
How does that compare to what came before? We've had big sky surveys for decades.
It blows them out of the water in terms of 3D mapping. This first data release from DI contains more than twice the number of objects with measured distances, spectra, than all previous 3D spectroscopic surveys combined.
Wow. More than double everything that came before in just over a year.
Yep. Take its predecessor, the Sloan Digital Sky Survey, a legendary project. Sloan took about 25 years to collect spectra for around 9 million unique objects. DISI did double that in roughly 13 months.
How is that even possible? What's the technology that enables that speed?
It's an amazing piece of engineering on the Mayall telescope in Arizona. Instead of looking at one object at a time, or even a few hundred, DI uses a focal plane packed with 5,000 tiny robotic fiber optic positioners.
5,000 robots.
Little robots, yeah.
Okay.
Each one is about the width of a human hair, and they can independently swivel and point a fiber optic cable precisely at the light coming from a specific, pre-selected distant galaxy or quasar.
So it measures 5,000 objects simultaneously.
Exactly. Each fiber pipes the light from its target object down to a bank of spectrographs. These instruments split the light into its rainbow spectrum.
And from the spectrum, you get the distance.
That's the key. By looking at how much the features in the spectrum are shifted towards the red end, and the redshift due to the expansion of the universe, scientists can calculate the object's distance very accurately. Redshift equals distance, essentially.
So you get a precise 3D position for every one of those 5,000 objects.
Right. And by doing this for millions of objects across the sky and at different distances, you build up this huge 3D map showing the structure of the universe over cosmic time. DSI is mapping from nearby galaxies all the way back to objects whose light has traveled for 11 billion years.
It's charting cosmic history in 3D. I heard one of the scientists involved called it Moore's Law for cosmology.
David Schlegel, yeah. And it fits, doesn't it? They basically maintained this pace where the size of our 3D cosmic maps gets about 10 times bigger every decade.
That's exponential growth.
It is, and it's only possible because the whole system, including the targeting of those robots and the initial data processing, has AI woven into it, making it incredibly efficient at selecting and measuring the most scientifically valuable targets, especially faint, distant ones.
Okay, so we've got precision doubling with AI and map scale exploding by orders of magnitude. But there's another crucial aspect: time. Some cosmic events happen fast and fade away.
Absolutely. This brings us to what might be the most urgent application of AI in astronomy right now: real-time detection of transient events, things that go boom in the night.
Supernovae, gamma ray bursts, things like that.
Exactly. These events are often incredibly important. They tell us about stellar evolution, the creation of heavy elements, even fundamental physics. But they can be brief. If you don't spot them within hours or days and get telescopes pointed at them quickly for follow-up observations,
You miss the crucial early data.
you miss the peak brightness, the early spectral features that tell you what's going on. And the problem is, we're about to be absolutely flooded with these things.
You're talking about the Vera C. Rubin Observatory.
Yes. Set to come online around October 2025, I think. Rubin is going to scan the entire visible sky every few nights. It's going to generate an unprecedented flood of data. We're talking about detecting hundreds of new transient events every second.
Every second. How can astronomers possibly cope with that?
They can't, not manually. No team of humans can sift through alerts coming in at that rate, decide which ones are interesting, and trigger follow-up observations. It's physically impossible.
So AI becomes the essential filter.
It has to be. That's why groups like the Sky Institute, the NSF Simons AI Institute for the Sky, are working flat out to develop what they call foundation models for astronomy. These are AI systems designed specifically to ingest and classify this massive, multimodal data stream: images, spectra, brightness, changes over time in real time.
And we already have examples of AI doing this successfully, right? Like that supernova SN 2023's K.
Ah, yes, SN 2023 scale, that's a perfect case study, a fantastic story.
Tell us about it. What made it special?
So astronomers were using an AI algorithm developed primarily at UC Santa Cruz. This algorithm was designed to scan through data from existing surveys, specifically looking for unusual explosions in real time.
Not just any supernova, but weird ones.
Exactly, and it flagged SN 2023 scalide literally within hours of the explosion happening. That rapid alert was crucial because it allowed astronomers to quickly get time on multiple other telescopes, big ones, to get detailed follow-up data while it was still bright.
Okay, so the AI found it fast, but what was unusual about this supernova? Didn't it look normal at first?
It did initially. The AI first classified it as likely a Type 2 supernova, which is the common type resulting from the core collapse of a single massive star. Its brightness started fading in a pretty standard way.
But then,
But then, as it was dimming, it did something very strange. It suddenly brightened up again, significantly. A major rebrightening weeks after the initial peak. That was the big red flag. That's not typical Type 2 behavior at all.
a second wind. That is weird. Did they figure out why?
Well, that rebrightening prompted them to dig deeper. They looked back at archival images of that exact spot in the sky from years before the explosion.
And what did they find?
They found that the star system had actually been gradually getting brighter for more than 4 years before the final supernova went off. This kind of long-term pre-explosion activity is almost unheard of for this type of event.
Wow. Years of warning signs before the Big Bang. So putting the pre-explosion brightening together with the later rebrightening, what's the explanation?
The interpretation is really quite dramatic. They concluded the explosion wasn't just a solar star collapsing. It was triggered by a catastrophic interaction between the massive star and a companion object specifically, a black hole.
A black hole triggered the supernova. How?
The idea is they were in a close binary system. The black hole's immense gravity started siphoning material off the massive star, or perhaps tidally disrupting it, pulling it apart. This interaction, this gravitational stress, destabilized the star over several years, causing that slow brightening, as material likely formed an accretion disk around the black hole and eventually pushed it over the edge into detonation. The later rebrightening might have been due to the supernova shock wave hitting material previously stripped from the star.
So this is direct evidence that a close encounter with a black hole can actually make a star explode.
It's considered the strongest evidence to date for exactly that scenario.
Yeah.
It's a mode of supernova triggering that's been theorized, but rarely, if ever, observed so clearly.
And the key was the AI catching it early and flagging the later anomaly, allowing them to get the detailed data needed to piece that story together.
Absolutely. Without that initial AI flag and the rapid follow-up it enabled, especially capturing the spectrum during the rebrightening phase, the crucial clues would have been lost. The event would have just faded, maybe logged as a slightly odd Type 2, and the black hole connection would likely have remained hidden.
It really highlights the need for that immediate unbiased filter. Humans might have glossed over the initial alert or missed the significance of the later bump amidst thousands of other alerts.
Exactly. The AI doesn't get tired, doesn't have preconceptions. It just applies the statistical model and flags deviations. For these fast, fleeting events, that capability is moving from nice to have to absolutely essential.
And it's fascinating to think that the same kind of AI needed to spot an exploding star interacting with a black hole could have applications much closer to home.
Oh, definitely. The researchers involved made that point explicitly. The core technology here is real-time anomaly detection in complex, high-volume data streams. That's a challenge in many fields.
Like what?
Well, think about medical diagnostics. Imagine an AI scanning through thousands of patient scans or vital sign streams, looking for that one subtle pattern that indicates the very early stage of a disease, something a human doctor might miss until it's more advanced.
Finance.
Or financial fraud prevention, yeah. Sifting through millions of transactions per second to flag the one unusual sequence that indicates sophisticated fraud. Even national security applications, monitoring complex sensor networks. The fundamental AI techniques finding the weird needle in the overwhelming haystack fast are highly transferable. The algorithms used for SN 2023D Quilt could, conceptually, be adapted for these terrestrial challenges.
So cosmic discoveries are directly driving innovation that could impact our daily lives. That's a powerful connection. Okay, we've talked about the science, precision, scale, speed, but none of this happens in a vacuum. What's the engine driving all this? The hardware, the computing power.
Right, you absolutely need serious computational muscle behind these projects. You can't process data from DSI or run those huge simulations on a laptop.
Where does this processing happen?
For major US-led projects like DSI, a lot of the heavy lifting happens at dedicated supercomputing centers. A key one is NRC, the Rational Energy Research Scientific Computing Center, run by the Department of Energy.
And NRC recently had a significant upgrade that boosted projects like DSI, didn't it?
They did. They deployed a new flagship machine called Perlmutter. named after Saul Perlmutter, one of the noblists who discovered dark energy.
And Perlmutter made a big difference.
A massive difference. The key architectural change was its heavy reliance on GPUs, graphics processing units, alongside traditional CPUs. For the kind of work DSI does, analyzing thousands of spectra simultaneously, GPUs are incredibly efficient.
Why are GPUs so much better for this kind of task?
It comes down to parallel processing. Analyzing a spectrum involves many repetitive calculations correcting for instrument effects, fitting models to measure redshift. GPUs are designed to do thousands of relatively simple calculations like these, all at the same time, in parallel. CPUs are generally better at complex sequential tasks.
So offloading the spectral analysis to GPUs just crunches through it faster?
And much faster. The reported speedup for processing DSI data on Perlmutter compared to the previous NIRC systems was nearly 40 times.
40 times. That's incredible. What did that mean practically?
It meant analysis tasks that used to take months could now be done in weeks, sometimes even days. It dramatically shortened the feedback loop for the science team.
Which enables that whole redshifts before breakfast idea.
Exactly. The pipeline is so optimized now. Data comes off the telescope at night, gets transferred automatically over high-speed networks to NERSC. Perlmutter's GPUs chew through the spectral analysis overnight, and validated redshifts and classifications are often back in the hands of researchers by the next morning. It allows for very agile science, like quickly deciding to reobserve an interesting object.
And it wasn't just US supercomputers, right? The UK team working on the DES precision analysis also needed heavy compute power.
That's right. They highlighted the use of UK national supercomputing facilities, specifically the DRAC, distributed research using advanced computing resources, which are funded by the government specifically for theoretical modeling and data-intensive science like cosmology. Running those thousands of simulated universes for AI training requires enormous processing power.
So we have the massive hardware infrastructure, and we have these huge survey projects. It feels like there's now this growing ecosystem of specialized AI tools for astronomy.
There really is. It's moving beyond just applying general machine learning techniques. People are building AI specifically tailored for astronomical data and problems.
Can you give us a few examples?
Sure. We mentioned the SKAI Foundation and models. You've also got things like Google DeepMind's AstroSim. This isn't just analysis. It's an AI tool designed to make the simulations themselves faster and more efficient, particularly for complex processes like galaxy formation or modeling dark energy effects. You can learn to approximate or speed up parts of the simulation that are computationally very expensive.
Using AI to accelerate the simulations that we then use to train other AIs, that's quite meta.
It is a bit.
Mm.
Then there's NASA's Examiner. This is a deep learning system built specifically for finding and validating exoplanets and data from missions like Kepler and TESS. It's particularly good at distinguishing real planet signals from false positives caused by instrument noise or other stars, something humans can struggle with.
And it's not just pure science. AI is getting involved in the practicalities of space, too.
Definitely. You see companies like Astroscale using AI to help track orbital debris space junk and develop autonomous systems for capturing and removing it. That's crucial for protecting satellites.
And even rocket landings.
Yeah, Blue Origin has talked about their orbital AI system, which uses AI for things like autonomous hazard detection during landing, helping the rocket identify safe touchdown spots and adjust its trajectory in real time. It's about increasing safety and reliability.
It really feels like AI is becoming embedded everywhere in space science and operations. But maybe the biggest shift is still to come in how scientists actually use these tools. You mentioned natural language.
This, I think, is the really exciting frontier for usability. The vision, pushed by groups like SKAI and another collaboration called SEMA, is that in the near future, scientists won't necessarily need to be expert coders to leverage these incredibly complex AI models and vast data sets.
So instead of writing intricate Python scripts,
You might interact with the system using intuitive natural language queries. You could literally ask the AI system something like, show me all the galaxies in the latest DSI data release that are between redshift point 1 and point 2, appear to be merging based on Rubin Observatory images, and show potential signs of hosting an active supermassive black hole according to Chandra X-ray data.
wow. So the AI would understand that complex request, query across multiple different data sets from different telescopes, run the relevant analysis models, and give you the answer.
That's the goal. to create AI agents that can understand scientific intent expressed in natural language and orchestrate the complex data retrieval and analysis needed to answer the question.
That would completely change who can do cutting-edge research. It lowers the barrier to entry enormously.
It democratizes it, exactly.
Mhm.
You wouldn't need to spend years becoming an expert programmer on top of being an astrophysicist.
Yeah.
And this has huge implications for education, too. Universities are starting to realize they need to change their curricula. If this is the future, then astronomy students need to learn how to work with these AI systems from the ground up. It means embedding AI concepts and tools into almost every astronomy class, not just having it as a separate specialized topic. The next generation of astronomers will need to be fluent in both the physics and the AI methods used to explore it.
Okay, this has been a fascinating journey through AI in cosmology. Let's try to wrap up with some key takeaways from everything we've discussed. It really feels like AI has fundamentally shifted the field.
It really has. It's taken cosmology from, careful observation and theorizing to something approaching industrial scale discovery, tackling that huge invisible part of the universe head on.
So, takeaway number one seems to be about precision. AI is letting us measure the fundamental components of the universe, like dark energy and dark matter, with dramatically improved accuracy. That doubling of accuracy from the DEIS analysis is a prime example.
Right. It's refining our basic understanding of what the universe is made of, tightening those constraints on the cosmological parameters.
Takeaway two, scale and structure. AI enables these incredibly large and rapidly growing 3D maps, like the ones from DSI, which are 10 times bigger every decade. And it's letting us visualize hidden structures, like those dark matter bridges connecting galaxies.
Yeah, it's moving beyond abstract numbers to actually mapping the cosmic web in detail, revealing the architecture of the universe, both visible and invisible.
And the third takeaway has to be time. AI is becoming the essential real-time filter for handling the data deluge from new telescopes. It's catching those fleeting, transient events like the black hole-triggered supernova SN 2023's Kalind, giving us crucial data we would otherwise miss entirely.
That real-time capability is critical. It ensures we don't lose unique insights just because we're overwhelmed by the sheer volume of data.
But as we finish, let's circle back to that underlying tension you mentioned, the one that AI hasn't just solved, but maybe has sharpened. The lumpiness problem.
Yes, this is the really provocative thought to leave people with. Multiple AI-enhanced analyses, particularly the precise weak lensing measurements from DES, keep hinting that the universe today is less lumpy, more smoothly structured than our standard model predicts based on the cosmic microwave background.
So we have this mismatch. The early universe picture, CMB, implies structure should have grown more clumped by now, but the late universe measurements, powered by AI, suggest it's smoother.
Exactly. And the AI keeps making those late-time measurements more and more precise, seemingly reinforcing this discrepancy. So it forces a really fundamental question.
Which is,
If this observed smoothness holds up, if future surveys with even better AI analysis confirm it beyond any doubt, what does it mean? Option 1. Maybe our bedrock theory of gravity, Einstein's general relativity, isn't quite right on the largest cosmic scales. Maybe gravity works slightly differently over billions of light years, leading to less structure growth.
modifying Einstein. That's
It is. Option 2. Maybe general relativity is perfectly fine, but there's some other unknown physics at play. Something happening between the time of the CMB and today, some new interaction, some property of dark matter or dark energy we haven't accounted for, that naturally suppresses structure growth and makes the universe smoother than expected.
So either our theory of gravity is incomplete, or there's some major missing piece in our understanding of the universe's contents and evolution.
That's the crux of it. AI has given us the tools to make these incredibly precise measurements, but those measurements are now pointing to a potential conflict at the very heart of our cosmological model.
Yeah.
Resolving that conflict, figuring out if gravity needs fixing, or if there's new physics hiding in plain sight, that's arguably the biggest challenge AI has laid down for the next generation of cosmology.